Hello everyone, and welcome to Recitation with Sohail. Today we'll be doing problem 40 from section 3.3 of the 10th edition of Boyce and DiPrima. We want to solve the differential equation given in equation 1, which is that t squared times y prime prime minus ty prime plus 5y equals 0. And we want to solve it on the interval t is bigger than 0, since we have to work on interval where this leading coefficient of t squared is non-zero in order to avoid the bad things that happen when your leading term disappears. Now, this is a second order linear differential equation, which is nice because we like linear differential equations. And this is actually an even more special type of equation called an Euler equation. It's similar to a constant coefficient differential equation, but this time instead of constant coefficients, our coefficients are polynomials, and specifically, it's t squared times y prime prime, and we could have an extra constant here if we would like, plus a constant, -1, times t y prime, plus just a constant times y. So this is like t to the 0 times 0 derivatives of y, t to the 1 times 1 derivative of y, and t to the 2 times 2 derivatives of y. Now, if we quickly take a peek in the textbook, they do discuss Euler equations in chapter 5, which you can see here in equation 2. They just show a general Euler equation. So alpha and beta are the constants, and whatever the leading constant was, they divided it out. And they do give a general formula for how to solve it, how to get the values of r, and how to, how the corresponding solution is x to the r. And they do discuss some of this in chapter 3 as well, but what I would like to do here is I want to show you how to solve this from first principles, or at least just how to reduce it to a second order constant coefficient differential equation using just the method of substitution, and then we will solve our equation. So hopefully you will learn how to solve an Euler equation in this video and how to perform substitutions when working with differential equations. Now, the substitution we want to make, this is actually given to us in chapter 3 of the textbook, if you go through exercises, is over here, x equals natural log of t. And when we make this substitution, we want to get a new differential equation based on some other function h, which is a function of x, our new variable. And specifically, this h of x, it is going to be y of e to the x. And the reason for this is that if x is natural log of t, then when I exponentiate both sides, I see that t is equal to e to the x, right? So t and e to the x are the same, just by definition of x. So ultimately, h of x is going to be the same as y of t. They're representing the same function. So if we find h, then we will effectively have found y, but we're hoping that when we do this substitution, when we view things from the perspective of h of x instead of the perspective of y of t, we get a simpler differential equation. And as we will see, this does indeed turn out to be the case. We're going to go from polynomial coefficients down to constant coefficients. Now, we know the relationship between h and y, h of x and y of t. But in order to perform the substitution, I need to also know the relationship between h prime and y prime, so I can get rid of the y prime up here in equation 1. I also need to know the relationship between h prime prime and y prime prime to get rid of the y prime prime in equation 1 as well. So I do still need to acquire more information before I can do the substitution. And there's one more point about which we need to be careful. In the beginning, if you look at equation 1, I just wrote y prime and y prime prime, and it was obvious that I was taking a derivative with respect to the variable t. And that's why I just wrote the prime. But now, we are working with two variables. There's x and t. So I need to be more specific about what my derivatives are. Because, for example, we see here that y, I could view y as a function of x, namely y of e to the x, or I could just view it as a function of t, y to y of t. Same for h, I could just say h of x or h of ln t. So if I just write a prime now, it's not obvious. If that prime represents a derivative with respect to h, a derivative with respect to x, or a derivative with respect to t. So in order to hopefully avoid confusion, I'm going to use the d by dx and the d by dt notation. So just be very explicit about which variable with respect to which I'm taking a derivative. And this is annoying. It is much faster to just write down the primes. It's more convenient. But I'm hoping that the extra precision is going to be worth the extra writing. So now, if we go back to our first goal, we want to know the relationship between h prime, by which I more specifically mean dh dx, the x derivative of h, with y prime, namely the t derivative of y. So I'm going to calculate it with the chain rule. I start with dh dx, and I know from back here that h is going to be equal to y of e to the x, right? So that's how I use the chain rule. I first take a derivative of outside function, so I take a derivative of y of t, and that's my dy dt. Then I take a x derivative of the inside function, dt dx. That is just the chain rule from Calc 1. So dy dt, I don't have to simplify that. That's what I wanted to appear. I want the relationship between dh dx and dy dt. And then dt dx, that just happens to be e to the x. Because if we go back up here, we see that t equals e to the x. So take x derivative, it's still e to the x. And then once again, e to the x is t. So that's how I finish the first equation and conclude that the relationship is dh dx equals t times dy dt. So we're off to a good start. What we have so far is that h of x equals y of t, and that dh dx equals t times dy dt. Now, I'm going to keep going. I want to find out the relationship between the second x derivative of h and the second t derivative of y. So I'm going to do the same thing. First, I notice that the second x derivative of h is, by definition, the x derivative of the first x derivative of h. And then we saw earlier that the x derivative of h, one of the many ways in which we could write it, is e to the x times dy dt. So that's what we're going to use here, e to the x times dy dt. And now I want to take an x derivative of this. And remember, dy dt is still a function of x as well as t, because t and x are related. So I have to use the product rule here. I am multiplying a function of x, e to the x, with another function of x, dy dt. Or if you want another function that depends on x, that is influenced by x. So I do my product rule, I leave the first term unchanged. Excuse me, let me say that again. I take the x derivative of the first term, so x derivative of e to the x is just e to the x, and then leave the second term unchanged, which is why I have dy dt over there. Then I add to that the derivative of the second term, so d by dx of dy dt, and I multiply that by the first term, which is now unchanged, so e to the x. Now, I got to the start of equation 4. To get to the second half of equation 4, you'll notice I didn't really touch the first term. The e to the x times dy dt has remained the same. And this e to the x on the outside of the second term has also remained the same. And now for the d by dx of dy dt, I apply the chain rule. So I first take the derivative of the outside function. So right now, dy dt, it's a function, we think about it as a function of t. So I take a t derivative of the outside function, which is why it became d squared y over dt squared. And then I multiply that by the x derivative of the inside function, which is t, in order to complete my chain rule. Now, if we go on, once again, the first term, the e to the x times dy dt, untouched. The e to the x on the second term, untouched. The d squared y over dt squared is untouched because we wanted that. We want the relationship between d squared h over dx squared and d squared y over dt squared. So I leave that untouched. dt dx, if we remember, t is e to the x, so dt dx is e to the x. And that's where this other e to the x comes from. Right? This, oops, I think I already used that color. So wouldn't I switch it to that one? This is corresponding to that. And then we remember that t is equal to e to the x. So we can just go ahead and, use the fact that t is e to the x to turn this e to the x into a t, and then e to the x times e to the x is t times t, which is t squared. I also did switch the order of the left and right terms here. In conclusion of all of this, all of these calculations, the second x derivative of h is equal to t squared times the second t derivative of y plus t times the first t derivative of y. Now we finally have all the pieces in place in order to go ahead and perform our substitution. So now, in equation 6, we start off with the original Euler equation that we were given. 0 equals t squared times the second t derivative of y minus t times the first t derivative of y plus 5y. I haven't done anything yet, just rewrote the equation. Now, I'm going to regroup terms a bit. I know I'm going to want this t squared, right? Or sorry, let me, I'll go with that color. I'm going to want t squared y prime prime plus ty prime. So I make that appear. I prepare myself to get the term that's going to turn into h prime prime. And then, in order to keep things even, I added a ty prime here, so I have to subtract the ty prime, which is why this negative ty prime turned into negative 2 ty prime. Alternatively, you could just check for yourselves that this ty prime plus this negative 2 ty prime is equal to this negative ty prime. So the left and right parts are actually equal to each other. So now that I did that, I can go ahead and convert that first term into h prime prime, where I'm being a bit sloppy here, but I'm assuming that in the beginning we understood what was the x and the t derivative, so now I can go back to being lazy and write my primes, and you know that this is the x derivative of h. Similarly, recalling that the first x derivative of h is t times the first t derivative of y, we see that this negative 2ty corresponds to just negative 2h prime. And then we also knew that h was equal to y. So that's why this 5y just turns into 5h. But in conclusion, we see that the result of the substitution is 0 is equal to h prime prime minus 2h prime plus 5h. So the resulting differential equation in h is a second order constant coefficient differential equation, which is something that we already know how to solve. That was in the beginning of chapter 3. So now we'll go ahead and solve it, and we see that the corresponding characteristic polynomial for that differential equation in h is r squared minus 2r plus 5. To get the roots, I just use the quadratic formula, negative b plus or minus square root of b squared minus 4ac all over 2a. Go ahead and simplify it, and I see that the roots are 1 plus or minus 2i. So that means the general solution to my second order constant coefficient differential equation in 6 is that h of x equals some constant, c1, times e to the x. So this is this x, right? I take the real part, and that's corresponding to the x in the power of e. And then the imaginary part, this 2i, that corresponds to the cosine of 2x and the sine of 2x. c1 e to the x times cosine 2x plus c2 e to the x times sine of 2x. Now, we did successfully solve for h of x, but that's not what we wanted. We wanted y of t. That's what the problem asked us for. H of x is something that we made up. So to finish off, we just have to convert our answer from x back into t. We know that y of t equals h of x, and x is ln t, so h of ln t. I'll go ahead and plug in the natural log of t into equation 9. You get c1 e to the natural log of t times cosine of 2 times natural log of t plus c2 times e to the natural log of t times sine of 2 times natural log of t. And lastly, I just use the fact that e and natural log are inverses. They cancel each other out. So this e to the ln t is just t. And then that other e to the ln t is also just t. So in conclusion, our general solution to the Euler equation is a constant c1 times t times the cosine of 2 times natural log of t plus another constant c2 times t times sine of 2 times natural log of t. So that's all I have for this problem. If you like it, give the video a like and subscribe.